I wish to thank the organizers for the privilege of contributing to Yang Mill 60. My talk is on Yang Mill's Kaluza-Klein correspondence, Path to New Physics. As I said to the panel day, just as the infinities in the Rayleigh-Jeans law signify the imminent birth of quantum mechanics, so do the infinities related to renormalization signify another imminent age of discovery. I don't think most physicists realize that. I turned it off. Okay. The abstract's in the book, so we won't go into that. All theories are approximations, suggesting that there is new physics. Everybody knows about the Kaluza-Klein correspondence. That's our pathway. Kaluza-Klein led to, of course, to string theory, so the alternative to what I'm promoting is what they're trying to do at the LHC. They want to use more power to test for reality beyond particle physics. Maybe people like Nima Akarni-Hamed and Lisa Randall are proposing experiments to hunt for string-type higher dimensions. Current view, I'm suggesting that there's more. We're working on some math. It's not presentable yet, so this is just going to be a brief axiomatic conceptual talk, so you'll have to bear with me. There's a few fundamental main premises. The first major one is that Planck can no longer be considered fundamental. So there has to be something then beyond Planck. I stand with Lisa Randall, who suggests there are infinite-sized additional dimensions. This stares in the face of Kaluza-Klein and string theory, which suggests that additional dimensions, if they do exist because we don't see them, are curled up at the Planck scale. That's not the only way of talking about the size of additional dimensions, but it's beyond the scope of this brief talk. So the third premise beyond Planck is there's a manifold of uncertainty of finite radius. We are able to predict at the moment that it's either a three-dimensional or six-dimensional manifold, which is compatible with Calabi-Yau 3 torus or a dual 3 torus. Until one or the other, which I'll get to in a moment, fundamental principles is you have to have a new definition of a singularity or a fermion vertex. And that entails a higher dimensional close packing of space-time. Until we finish figuring out how to close pack it, we don't know if this manifold will be 3 or 6 dimensional. Another way of looking at that, we have our little Euclidean Minkowski space surrounded by this manifold of uncertainty. Just conceptual. Oops, I did it again. Just another way of looking at M theory. This is a beginning of a metaphor for the least unit. It has a threefold symmetry, and we're working on a quaternionic model. As most of you know, string theory adds a factor to the Planck concept, that of string tension. The original hadronic form of string theory, which we use, had a variable string tension. That's important in this model. The new version has a fixed string tension. Just one point I want to make about this. String theorists are looking for one unique compactification that will reduce to the standard model. In our model, we have this continuous state, which is one of the very important keys to this, but it is a very hard thing to define. I have trouble defining it to people in an hour, so won't be able to. The only thing I'll be able to say about it is that we have a continuous state compactification that goes from 12 down to 0. It's like these least units are like Kähler manifolds. Calabi-Yau manifolds are also reduced to Riemann spheres. You know about the 0 point and the infinity point in the Riemann sphere. So when it gets down to 0, these least unit groups flip back to infinity and the cycle starts over again. I don't have time to say much about this. Whoops. This is part of our redefinition of a fermionic vertex. Instead of the standard fixed vertex, we have in here a Witten vertex, which allows this structure to move. The standard model has a 0-point field of virtual particles allowed to exist for the Planck time. If we model instead with additional degrees of freedoms from higher dimensional body, we have, this is an exaplex. I'm using it as a metaphor. It comes from chemistry. This would be a 0-point field particle. These would be virtual particles winking in and out of existence at the Planck scale for the Planck time. An exaplex exaplex never goes to ground. Because these two particles, it only exists if these two particles bond. So this gives a beginning of a mechanism, and unfortunately it would take me an hour to explain it to you, and I apologize for that. I just want to give you a flavor of something that may be coming. This allows the action principle of the unified field to come into 3 or 4 space, like kind of like a lighthouse flashing. You know, it's a relativistic model, so we don't have the unified field. Just as the laws of quantum mechanics were invisible to classical mechanics, so are the tools of unified field mechanics invisible to quantum mechanics. So there'll be a new action principle, and this is another metaphor for brain topology in higher dimensional space, where these will be, this is also going to be like that exaplex gating mechanism, where these will, with string tension, these will flip back and forth, and they're able to go through the different scales of brains. Fortunately, I was very pleased on panel day when one of the Nobel Prize winners has said a crazy experiment. So that means my model is on the way. I have a Nobel Prize winner who called it a crazy experiment, unless even Einstein, after he had his annus mirabilis and proposed the photoelectric effect, as said, people call him a moron and idiot to his face. So, and Gandhi said, first they laugh at you, then they criticize you, and then you finally win. So I have, fortunately, an experiment. The timing is good for this. Some of you may have heard of Chandler's experiment in 2012 at NIST, the National Institute of Standards and Technology in Washington, D.C., where he took he'd been working on experiments like this for 10 or 20 years before that, but the effect was so small in pure hydrogen that it was ignored. But in this experiment, he stripped all the electrons off but one in titanium, so he had a hydrogen-like atom. And the effect was large enough that now people have started to take notice. So without QED has been sacrosanct for a long time, considered the best model in physics. So now we're beginning to violate that. So it gives me a little crack in this to propose this type of a model that I'm proposing. This, I left out something I wanted to say. I did say that the manifold of uncertainty was either 3 to 6 dimensions long. Because they're larger than Planck dimensions, We can make the initial prediction using the standard equation from the late 1800s for predicting the volume of hyperspheres. So we can predict that we can take the volume of a 4, 5, and 6-dimensional hyperspheres and use those to predict new spectral lines in hydrogen below the lower spore orbit. That sounds like nonsense, and when I first thought about it, I thought that was absurd too. But these cavities in the manifold of uncertainty that open up into the higher dimensions, as they open up, there's a little more volume. So as you remember your high school chemistry, the first spore orbit is a 1/2 angstrom and the second one is 2. So we can send in our RF pulse at NIST, hopefully. If they have all the equipment, all we got to do is get in their queue. We'll get reflections back in for Bohr orbits between the 1/2 angstrom and the 2 angstrom. We're predicting 2 or 3 of those. When we finally cross into the large infinite-sized extra dimensions, just as the outermost electron of an atom, when it's charged, goes off into infinity, when we finally cross the manifold barrier, that we won't find that last either 3rd or 6th predicted spectral line because it will go off into infinity. Metaphor, quick metaphor for the experiment. The other thing that's added to this, which I wish I could define, is there's going to be a beat frequency of space-time, which doesn't exist in the standard model. We have a Planck scale as the basement of reality, a fixed barrier. But in this barrier, because it opens up, at least till you get through the manifold of uncertainty, like a holophone or a lighthouse, the only way it's possible to do this experiment, if this type of beat frequency in space-time does exist, we need a Dirac polarized vacuum. We're going to punch some holes with an incursive oscillator. We shake the electrons, which are shaken such that they shake the nucleons. And we're using hydrogen, so we would set this up for hydrogen. And of course, it's the simplest. Any other atom would make this more difficult. Then you want to have that so it shakes space-time such that it will be in resonance, will be in tune with this beat frequency of space-time. I know this all sounds preposterous at first glimpse, but it's a paradigm shift. Imagine you were classical mechanics and somebody threw you 20 years into quantum mechanics. It would sound just as bad. But it's ultimately going to be that simple. We'll have a simple resonance that will tune itself to be able to pass through. I should just say one more footnote. Everybody knows that uncertainty principle is sacrosanct. It's been proven for the Copenhagen interpretation. Well, this is something else. If we do something else with a different view of space-time, doing the same way we measure things in quantum mechanics, you would never find this without this other type of beat frequency in space-time existing. I actually have 14 experiments. At the time I wrote this slide, I just described 9. Some of them will relate to biology. Some of you heard of the prion for mad cow disease. We can put a little Hadamard gate cavity in space-time and use this energy of the unified field to see if we can make a conformational change in the prion. But all this is for the future. And again, metaphorical. They don't really apply directly to the math, but they're just classical harmonic oscillator quantum, and down to the important one is going to be this incursive oscillator. The size of delta t will be the size of the hole you're able to punch in space-time. If you go into an auditorium, there's places you can see into infinity and places where the chair gets in the way. When we set this to the infinity point, we'll be able to send our signal in, and if it reflects back, we'll have found a new spectral line. I think that's the rest we don't have time for. If I have one more minute, I'll make one brief footnote. When does a theory in physics become an absolute truth? I don't know very much. I only know of one. Newtonian classical mechanics when it's falsified. Classical mechanics has been falsified. It's an absolute truth in the regime that it describes. This model, if it's correct, we will falsify quantum mechanics. It'll become an absolute truth in the regime that it describes, and we will go on to unified field mechanics. One more footnote, I almost forgot. In honor of Professor Xian Yan, I want to coin a new term. You all know of semi-classical limit. We will have a new thing called the semi-quantum limit. And I don't have time to say anything else, but in the future there'll be stuff that we'll write on this. I'm putting a team together. If any of you want to be part of this, please contact us and we'll see how we can mesh together. Thanks for your time.
If I think of Newtonian mechanics, then I say, well, that's rally. It's the velocity.
Precisely. That's what allows it to be falsified. It's that regime below relativistic.
Which is the parameter I should be thinking of, or what you have to say.
For falsifying quantum mechanics?
Yes.
The main one would be the uncertainty principle. We will, in order to do this experiment, you have to surmount and violate uncertainty. So there's a way of, this experiment doesn't work unless you surmount the uncertainty principle. So that is one of the main, and Bohm and Kramer were useless in the standard model. When we elevate them to this higher dimensional space, they become very useful. The quantum potential becomes a super quantum potential, correlating with the force of coherence of the unified field. This whole Calabi-Yau mirror symmetric stuff, Kramer becomes important in building, starting from force space and building higher dimensional space on Wheeler-Feynman, which led to Kramer, so that we're going to have this structure. There's so much more to this. A quantum state in three space is a resultant. In knot theory, it's the shadow of like, say, like a trefoil knot that doesn't cross over in higher dimensional space. So in this Calabi-Yau mirror symmetric up to 12 dimensional, we add a 12th dimension that string theory doesn't have because of the control factor of the unified field. There are copies up there, so you have, this opens a can of worms, but the highest one is causally free under certain conditions of the one in the three-space box. So that's the one that's going to allow you to run a quantum computer without decoherence, because this one up here, whatever you do to this one, if I shake in front of a mirror, it shakes the image. But if you have one that's causally free, as it's being passed like a baton up to this other one, whatever, I can input and read out up here without affecting the one in the box. And if they're all cycling through, anyway, that's a bigger can of worms than we have time for today. But all of this stuff, it works into this model. But as you said, the main one is surmounting uncertainty.